Hello everybody. Today we're doing polar coordinates, and polar coordinates should come quite easily to everybody, given how similar it is to writing, say, like trig form of an imaginary number, or even writing a vector in terms of magnitude and direction. Basically, it consists of 2 points. The first being an r value, the second being a theta value, theta being the directed angle, r being the directed distance. So, it's very much just taking those two pieces of information that were crucial, like I said, in writing a vector given direction and magnitude, or writing the trig form of an imaginary number. It's still those two important pieces of info. You're just kind of presenting them differently, graphing them on a polar coordinate plane. Yes, that just explains that. So let's just jump right into an example of it, because I do think you're going to pick it up quite simply. If we have a specific point, r comma theta, so directed angle, directed distance, it's 2 and pi over 3, it's going to be 2 units from the pole, and we consider the pole in a coordinate system, a polar coordinate system, to be the origin. So 2 units from the origin on the terminal side of the angle theta equals pi over 3. So we know pi over 3 is, if we were to change that into degrees, it's 60 degrees. So it's going to be, somewhere like this. It's going to have an r value of 2, and this angle right here will be pi over 3. And it's really that simple. You can give a more accurate representation right here. We have a particular angle, directed angle, and this is going to go on forever, but our particular point is right here, 2 units away from the pole. Okay? So it's a little bit different than graphing, something on a regular Cartesian coordinate plane. But everything's, what is the directed angle, and then how far away from the origin am I going. And it's really, that simple. It doesn't need to be any more complicated than that. Let's take a look at another example here. Let's say that I have a particular point, r theta, that's 3 and negative pi over 6. Alright, so the direction angle is negative, so that means it's going to be going, something like this, below kind of that x-axis. So this angle here will be negative pi over 6. And it's going to be 3 units away from the pole of the origin. So on this directed angle, it will be 3 units away. So again, let's take a look at a more accurate depiction. And there it is. This angle right here is negative pi over 6. And we go 1, 2, 3 units away. That's where our point is. Last example of this kind, we have a particular point r theta that has a directed distance of 3, and the angle is 11 pi over 6. Now some of you might catch right on to this and say, well, 11 pi over 6 is the exact same thing as negative pi over 6, which was what we had here. We had still a directed distance of 3 and angle of negative pi over 6. So isn't this going to show me the exact same graph? And actually, yeah, it is. It's going to show you the exact same thing. Instead of moving from this axis here and going down negative pi over 6, you've just gone around and over to the exact same point. And your directed distance is still 3. So this is a way that we can describe a one particular point in this coordinate system in 2 different ways, which is about what we're going to go into in a second, which is multiple representations of the same point. Before we do that, though, I would love it if you could try exercise 9. Whoa, that's a messed up 9. Exercise 9 from, this is section 9.5. Try that out. Make sure that you feel comfortable with something like graphing these things. and then we'll move on to representing them in multiple different ways in the part that'll get just a little bit more in depth. Alright, so hopefully you had no problem with exercise 9, and we can move on to this next example, which is giving a point with a directed distance of 3, directed angle of negative 3 pi over 4, and all I want to do is just represent that 3 different ways. Alright, and there's a couple different things that we can do to make this happen. As you can imagine, like when we did multiple angles in trigonometry, if I wanted to, I can always take theta and add 2 pi to it. Basically, rotate it completely around the entire polar coordinate system, and it'll land exactly right back where it needs to. What's another thing that I can do? Well, this right here, this r value, I keep saying that it's a directed distance, and that's because the positive and negative value here does matter. This 3 means that it's going in the positive direction of 3, in the direction of the angle. But if I make that negative, and I have it go in the opposite direction, I could just add, I could add pi to my theta value, and that would get me the exact same angle as well. So all I do is make r negative, and then I take theta, and I add pi to it. So that's another way that I could represent it. In the first case, I didn't touch r. I just added 2 pi. Second case, I made r negative, and I added pi. What's another way? Well, I could also do the exact same thing. Make it negative, but this time subtract pi. That could work as well. And yeah, why don't we just stick with that? I think that's enough. So let's take a look at this particular one. Let's say for this example I decided I wanted to just add 2 pi to my angle. Well, that means that another way I could represent this would be 3 comma 5 pi over 4, and that's another representation. Let's say I wanted to make r negative, so negative 3, and then I have to add pi to it. That's going to bring me to pi over 4. Or I could make r negative, negative 3, and I could subtract pi from it, which brings me to negative 7 pi over 4. Alright, so what I did there was, we call this 1, 2, and 3. I did 1, and 2, and 3. All 3 of these different ways, just to represent the exact same point in multiple different ways. Alright, why don't you take a look at exercise 11, and that'll be doing that exact same thing, just to get used to the idea of looking at these things in different ways and recognizing the patterns between them all. Alright, once you're all set with that, we can move on to how we would convert between our regular Cartesian XY coordinate system and these polar coordinate systems. Alright, again, everything kind of comes back to this trigonometry, this idea of the triangles when we are doing conversions. So if I think about the pieces that I have in the polar coordinate system, I have r values and I have theta values. So if I want to convert, I basically have to convert r's and thetas to x's and y's, and those are the relationships that I need to create here. So if I'm looking to create what are x's and what are my y's, if I have polar and I want to go to rectangular, sometimes rectangular is referred to, I've said Cartesian or XY. So I have r's and thetas and I want to represent them with the x. So how can I represent this x value? If I'm trying to create the points of an xy coordinate system with so much x, so much y, and then I can plot a point, how can I represent this x value in terms of the triangle that I've created here? Well, it always kind of comes back to this idea. If I do off to the side here, if I say something like cosine of theta equals x over r, that's a true statement given this triangle, and I can isolate x to say x equals r cosine theta. And I can do the exact same thing for y. If I write over here that the sine of theta equals y over r, this is a true statement given this triangle, and I can isolate y to say that y equals r sine of theta. And that's exactly how I convert from polar to rectangular. Right, now what about going from rectangular to polar? If I'm given an xy and I want to find the r and the theta, well, we've done this before. Whether it was trigonometric form of imaginary numbers or vectors, it's going to be the same type of idea. How do I find an r? How do I find the theta? Well, the theta value, if I want to look at this triangle, given the x and y, because x and y is what I will know. If I know the rectangular or the Cartesian coordinate points, x and y is what I know. So the only way that I can really do that is if I say that the tangent of theta is equal to the y over the x. Right? So if I want the theta value, I have to take the inverse tangent of y over x. And we've done that so many times. And then the r value. How can I go about getting the r value? If I know I'm starting at 0, 0, and I'm ending at this xy point, the simplest way to find the distance is the distance formula. So yeah, I'm going to be doing the square root of x squared plus y squared. Okay, so it's all this conversion stuff is all things that we've done before. It's all things that we know. It's just a matter of applying it to this kind of new idea. But it's still, will come very easily because we've done it before. We've done it so many times. All right, so let's do a really simple example, and then I'll give you one to try. I'm looking at a polar equation, 2 comma pi. So I have a directed distance and I have a directed angle, and I basically want the xy off of this. Now, if I'm trying to do that, technically what I would have to do is I would have to say that x is equal to r cosine of theta, which is what we just said before, and y is equal to r sine of theta. And this is an easy one so that we can see, intuitively I know what the answer is going to be, but how does it work when we actually put in the values? Well, what is the cosine of pi? The cosine of pi is going to be negative 1. So 2 times negative 1, my x should be negative 2. Now what's the sine of pi? The sine of pi is 0. 0 times 2 is going to get me 0, so my xy should be negative 2, 0. Right? And like I said, we could see that intuitively, because obviously this point is right here, 2 units away from the origin. It's going to be negative 2, 0. But it's good to see the way that this works with what we just talked about as well, and knowing for a fact that we know that it's true. If you could try exercise 17 and exercise 35, that'll bring you both directions, from polar to rectangular, from rectangular to polar. Try them out and just make sure that it's comfortable, and we'll go over that and look at it next time. Now, equation conversion gets a little bit more dicey. Going from points and everything, it's all stuff that we've done before. It's not too crazy, but the equation conversion requires a lot of ingenuity, right? Because the ideas are the same and you're substituting the same values, but once you substitute, we go back to solving trigonometric equations or simplifying trigonometric equations, that stuff from chapter 5 that everybody loved. And it was, it requires a lot of, well, maybe I can do this, maybe I can move that, maybe, I can try this, and it's a lot of independent thought. It's not so much algorithmic. So we're going to look at an example of just y equals x squared. All right, a very simple equation, and we're just going to rewrite it and show how something that starts off so easy requires a little bit of movement. So this, you remember, y was equal to r sine theta, so that's where this comes from. And this was x squared, and x was equal to r cosine theta. Alright, so this whole first thing was just substitution. It was saying, I know that I have a relationship between y and r sine theta. I know I have a relationship between x and r cosine theta. Alright, so that's all that was. And that's the easy part. That's, the simple conversion. After that, it's the simplification that makes it difficult. And a lot of people might be thinking, I have no idea how we got from this equation to the next one, because they just look so different. Well, this is where that simplifying and solving trigonometric equation stuff comes in. What we have to start to think of here is that I have r sine theta, and I have an r squared cosine squared of theta if I apply the square to both terms. Okay, so now basically what I want, if I'm converting this into polar, is I want r by itself. So how can I go about getting r by itself if I have it on both sides of the equation? One side's squared, one side's not. What is it that I could possibly do? Well, you could go two different ways. You could divide both sides by the sine and try and get r by itself on this side, or you could divide both sides by cosine squared, try to get the r squared alone. I think I'm going to go with the second one, just because I feel like it might be a little bit easier. If I divide both sides by cosine squared, then what do I get? What happens there? If over here, these things are going to cancel out, I'll get r squared. And over here, well, I just keep that simple for now. R sine of theta over cosine squared. Now let's divide both sides by r. I think that's going to be easier because when I divide both sides by r over here, this one goes away. So I have sine over cosine squared equals r, because I've divided this side by r as well. And now, lastly, all I have to do is take a look at this fraction over here and realize that what I'm looking at is sine over cosine times cosine, and that equals r. So sine times this imaginary 1 is equal to cosine times cosine. So I could say sine over cosine, well, what's that the same as? That's the same as tangent. And 1 over cosine, what's that the same as? Secant. So tangent times secant equals r. Alright, so all of this simplification, all of this rewriting just to make this thing as simple as possible. And we go back to that chapter 5 stuff, and it's going to be a little bit harder for some people. I know that that wasn't the easiest thing in the world to do, but we will get there. Let's see, if we could try out let's say exercise 91. After I show you a couple more, we're going to try exercise 91. So I'm going to do 3 more examples, A, B, and C. Just take a look at, it's kind of like 3 different relationships as to how this works. So the first one, r equals 2. So this time we're going from polar into rectangular. Oops, that was right. R equals 2. So that equation is technically just a circle. It's every single angle that is a directed distance of 2 away from the origin. Alright, so in terms of rectangular, what type of equation are we looking at there? Well, it's a circle. So I should be looking at some sort of equation for a circle centered at the origin. So what type of relationship can I use for that? Well, if I'm looking for the equation of a circle, I know that it says something like x squared plus y squared equals r squared if it's centered at the origin. So do I have a way to relate my particular r value to x squared y squared, and what is technically r squared if the radius is 2? Okay, so let's say I square both sides. So r squared now equals 2 squared. Okay, well the right side of the equation now says radius squared. So that's good. I have part of it. So now is there a way that I can relate r squared to x squared plus y squared? There is, because when we go back and I look at my conversions from polar to rectangular, whenever I wanted to find that r value, that distance, I was going to convert it by saying x squared plus y squared. So in fact, I can just convert x squared plus y squared in the place of r squared, and I have my rectangular equation right there. Alright, so I did two things. I squared both sides, that way I could get radius squared on the right here, and then I converted r squared to be x squared plus y squared, just using distance formula. Is essentially what we did. You could think of it as distance formula or Pythagorean theorem for when we're converting from polar to rectangular. Alright. B represents, the equation said theta equals pi over 3. And what that represents is a solid line of any distance. It could be any distance from the origin, but they will always create an angle of pi over 3 with the axis. So the question here is, how do I possibly change this into rectangular coordinates using the information that I have? Well, what was the way that I had to change over a point given a specific angle? Well, it had something to do with tangent, right? So right here, something that I could say is that tangent of theta is supposed to be y over x, right? So I could write that the tangent of theta equals the square root of 3, right? If theta equals pi over 3, then the tangent of theta equals the square root of 3. Now, from here, what I can do is say, well, if tangent of theta is supposed to be the y value over the x value, right, then that means that y equals the square root of 3 times x. Alright, and then from there, that's my, finished rectangular equation. I'm completely done at that point. In our last one now, we're looking at a different type where it says r equals secant of theta. And this one is kind of more of a function. The first one said r equal 2, the next one said theta equal pi over 3. This one says r equals secant of theta, which is a straight line. Alright, so in this one, the type of relationship that we want to look at is that r cosine theta equals x. And the reason I'm going for that one is because there's a relationship between cosine and secant. So what can I do to make secant not appear in here, but instead have it be cosine? Well, let's see. If I were to multiply both sides by cosine, okay, I'm going to put that in a different color here. Multiply both sides by cosine, then I get r cosine of theta on this side, And over here, cosine times secant just gets me a 1. Awesome. I'm in a really good place right now because I know that r cosine theta can just be replaced with an x. And x equals 1 is a vertical line at 1. That's perfect. I have completely finished this one. Alright, so like I said, we're going to try exercise 91. And do your best with it. I know that these can get a little bit tricky because they do involve a lot of new independent non-algorithmic thought to them. So give it your best shot, and we'll go over it, try a little bit in class next time.